All right, what's up, everybody? Welcome to part two of chapter 23. So this is all in one homework assignment. Covers chapter 23. We'll split it up into two parts. Again, a little bit longer this semester as far as the homework goes. So, hopefully we'll give ourselves a little more time. And if you haven't watched part one, obviously you want to watch part one. It'll be the first four problems. And in part two, we'll go over the second four problems. And yeah, I think just generally you want to give yourself a little more time. If you can do, if you could do part one day and then maybe save part two for the actual day that the homework is due, you'll give yourself a little more room, especially because homework is due on a Monday, right? So beginning next week, homework is due on a Monday, and if you're saving all of it for Monday, that's going to make for a pretty long day. Okay, so yeah, so we did one problem that was an application of Gauss's law. We did the rod problem, and I derived the electric field equation from that in the last video. That was sort of the last one I left off on. And today we're going to talk about a few other applications, and then at the very end, we'll go ahead and review. We'll give a list of the electric fields that come out of Gauss's law. So in truth, a lot of Gauss's law is just coming up with different definitions for the electric field and knowing when to apply them. So the first concept that we want to look at is a charged non-conducting sheet. So for a charged non-conducting sheet, here's your sheet. You have charge that is distributed throughout the inside of the sheet. I'm looking at it in cross section. So imagine the sheet is coming out of the screen and going into the screen. And it's also just kind of like infinitely long and to the right and left and coming out and going in. Now what we do, maybe we'd like to give this sheet a little bit of dimension, right? So it's going to keep going out like that. And the way that we actually perform Gauss's law on this sheet, first thing we need to do is denote the direction of the electric field. Since the sheet is flat, if we look at the rod problem from the last video, we mentioned how for the rod, the electric field points radially outward from the rod. With the sheet, you'll have a similar thing, except we can even take it a step further and say that the electric field will only point perpendicular to the sheet itself. So for instance, it's only ever going to point up like this or down like that. You'll have no component that is like at an angle to the sheet itself. It'll always just be perpendicular to the area, right? This is an area that's going in and out. Okay, so how do we actually do Gauss's law with the sheet? Well, remember the whole point of coming up with the Gaussian surface is a mathematical tool that we've invented, but we just want to design some 3D surface that satisfies two conditions. One of them is that the area is easy to calculate. And then the other one is that we'd like to draw this surface so that the electric field is perpendicular or parallel to its sides. So in this specific problem, what we would like to do is maybe have a surface that's like this, right? Up at the top. And then we'd probably also, want a mirror image down here at the bottom. Now we want to create a 3D shape, so we ultimately also need some other sides. But the nice thing about the sheet is that if I were to have, say, just a cylindrical, or not a cylindrical box, but a rectangular prism like this, then these vertical sides are going to be parallel to my blue electric field lines there, which means that the flux through those sides is automatically zero. This goes back to the very first problems that we did in this homework assignment. All right, so this thing is called a Gaussian pillbox. You don't need to know that. You don't actually need to know how this derivation takes place, but I'm still going to go over it because it's worth knowing like why this is in Gauss's law chapter, why we're covering Gauss's law at all. So the only faces that have some flux, to go back to our problems that we did way back at the beginning, we only need to consider the faces that have some electric field perpendicular. So that's just going to be this top face here and this bottom face down here. And great, I can use Gauss's law, right? I know how to do Gauss's law. Gauss's law just tells me that the sum of the E dot dAs over all of these has to be equal to the charge enclosed over epsilon naught, or our net flux has to be equal to the charge enclosed over epsilon naught. So to write that out then, I have the net flux, which is equal to the sum of the EAs, with a little bit more. We say E perpendicular, and we have some absolute value. We know that there's a plus or minus out front, is equal to Q enclosed over epsilon naught. All right, so for this one, as I mentioned, we have no electric field perpendicular to any of the four sides other than any of the other four sides. It's just those two yellow sides which have electric field going through them. And we can just say that they have an area of A on each of them. And they're going to have the same electric field passing through them. And of course, we want to solve for that electric field. And the area of each of them, we're actually just going to leave as A. So what we end up with when we plug that in is we just have EA plus EA. So we just have 2EA on the left-hand side. And then on the right-hand side, we just have the charge enclosed over, whoops, epsilon naught. I'm running out of room just a little bit. Great. So now I just want to solve for E, right? And if I do that, I have E is equal to the charge enclosed. I'm just going to write Q over 2 epsilon naught A. Now, just as we did in the last problem, remember we ultimately wanted to replace that charge. We said charge over length is actually a lambda. That allows us to sort of generalize out to however long the sheet happens to be, an infinitely long sheet. Well, that was a rod. With the sheet, we want to do a similar thing, but now with the sheet, the charge is distributed over this whole area, right? And the thickness of the sheet. So instead of doing charge per length or linear charge density, we're going to do charge per area or area charge density. And that would be just charge per area. And we call this value sigma. And so we have our electric field from a sheet. It's always just sigma over 2 epsilon naught. So this is for a non-conducting sheet. And we have two different types of sheets. We have non-conducting, where you have charge distributed throughout a sheet. The other type of sheet that you can have is a conducting sheet. And when you have a conducting sheet, instead of having flux to the top and the bottom, actually all the charge will be distributed along the surface of the sheet. You'll only have electric field on one side because the conducting material will conduct and act as a cage and prevent charge from building up on the other side. And thus, instead of having a 2EA on the left-hand side, you'll just have EA, and the electric field will be different. So I'm going to write them both right here because you're going to have to use them depending on the problem. First thing you need to do whenever you have a sheet is determine, is it conducting or non-conducting? So for non-conducting, we have electric field is equal to sigma over 2 epsilon naught. And for a conducting sheet, we have that the electric field is equal to sigma over epsilon naught. Sometimes they won't explicitly say conducting. Sometimes they'll say metal. Metal is a conductor. They will almost always tell you non-conducting. I can't think of a synonym that you'd be responsible for non-conducting. I guess you could have like plastic or something, but generally they're going to tell you explicitly non-conducting, but they won't always do that with conducting. So just be aware a metal sheet is also a conducting sheet. Okay, so what is the direction for this electric field? It's going to point away from a positive sigma and toward a negative sigma. And that's basically the long and short of it. So E away for positive sigma, and E is going to point toward for negative sigma. The most interesting part, I think, of this formulation is notice that there's no distance variable. It doesn't matter how far we are from the sheet. It only matters what the charge density is on that sheet. And it'll be called a surface charge density or an area charge density. And yeah, so direction is really the entirety of these problems. These tend to be on the easier side of the problems that show up in this chapter. So let's go ahead and do one. It'll be problem number 5, where we have two conducting sheets. And they have the same charge density. and they ask us to find the electric field above, between, and below. So let's go ahead and set up our sheets. We have these two sheets, and this one, and we have this one, and they're both going to have the same positive sigma on each of them, and of course everyone will have a different sigma, but let's go ahead and give them names. We'll just call this sheet 1 and sheet 2. You could do sheet top and sheet bottom if you want. And we just need to look at the three different regions, and we just need to consider the direction of the electric field from each. We have two sheets, they'll each produce an electric field, and we have to add them with superposition using vectors. However, because these the electric field in these is just sigma over 2 epsilon naught, because they're non-conducting sheets. This is just sigma over 2 epsilon naught, and it points away from the sheet always. There's nothing to worry about with angles or distances or anything like that. So let's go ahead and, first of all, I'm just going to draw the directions for the electric field in each region: above the top sheet, between, and then below. So above the top sheet, we have the electric field from sheet 1 that's going to point up. So that's E1. And we have the electric field from sheet 2 that's also going to point up. That's E2. If I need to find the total electric field, then the E total will just be, whoops, E1 plus E2. And so we have sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which is 2 sigma over 2 epsilon naught. And of course, you can cancel out your 2's if you like. The reason I'm doing this step in between is because you end up with sigma over epsilon naught, but it's not because they're conducting. These are non-conducting. I just had 2 of them, and that's why the 2 canceled. Okay, I just want to point that out. All right, and then we go to the next region. Our next region is between the sheets. For sheet 1, the electric field is going to point away from sheet 1, which means that it's pointing straight downward. That's E1. And sheet 2 is also going to have electric field pointing away, so it is going to point upward. That's E2. So our E total for this region is E1. Actually, E1 is negative, right? Because it's pointing downward. So we have negative E1 plus E2. Since they're both sigma over 2 epsilon naught, if I have one positive, one negative, this is equal to 0. All right, go into our last region. The electric field from sheet 1 up at the top is still going to point away, which is still going to be downward in this region. There's E1. And the electric field from sheet 2 is also going to point away. Now, since we're below sheet 2, that electric field is going to point down. So that's the E2, the electric field from sheet 2. And yeah, now we just add those two together. Notice they're both pointing down, so they're both in the negative y direction. So our E total now is just negative E1 minus E2, or plus a negative E2. And just as we had in the first region at the top, we have negative sigma over 2 epsilon naught minus sigma over 2 epsilon naught, which gives us negative 2 sigma over 2 epsilon naught, which is just negative sigma over epsilon naught. All right, and there you have with a sheet how to deal with those. This is, for my money, I think the simplest calculation for the electric field, again, because there's no distance variable. And we know that the direction is just always perpendicular to the sheet, which is greatly helpful in calculating these different electric fields. Okay, so let's go to our next problem. Our next problem is also going to be a sheet problem. This one we're going to get a little more complex with our setup. So we have our vertical sheet like this. That's going to be charged up with some positive charge distribution. Oops. I think it's better if I use a little bit of green just to show that that's the sheet right there. And then we're going to attach a ball by a string. Weird. And that ball is going to have both mass and charge. Okay, what is going on here? I'm going to move mass and charge actually, so it's out of my way. I'm going to put it in here. Mass and charge. So what we're setting up here is we're setting up a forces problem. And I'm not sure that they say consider the gravitational force of the ball and assume that sheet extends far vertically and into and on the page, right? So assume it's infinitely long. And we're given the angle as well. We're told that everyone will have a different angle here. Mine happens to be 40 degrees. But what we want to do is we want to consider the forces here. Okay, so the first thing is let's do our physics 2 first. So the physics 2 tells us that the electric field is going to point away from this sheet. And since this charged particle is in this electric field, the charged particle is going to feel an electric force. All right. To put this a different way, imagine there were no electric field here, then the ball should just like hang down here. The only reason why it's being pushed outward is because there's some charge on this sheet that's creating a force on the particle. Now, we also have some physics 1 here. We know that this particle has some mass, so it's going to have a weight or a force of gravity directed downward. And then there's a string attached to the ball, so there's going to be a tension along that string. So that's our physics 1 that we're tying into the physics 2. Now, just to finish out our physics 2 right now, we could, well, no, let's, I think the proper order here is to, no, yeah, I had the right idea. Let's finish out the physics 2 part first, and then we can go ahead and solve the problem. So the physics 2 part is the electric force, right? How do we calculate that electric force? I have mentioned this a little bit. We've worked with this just a little bit, but in deriving the electric field, we took the force divided by little q, the charge that was experiencing the force, and that gave us the field. When I reverse that relationship, then I have that the electric force is equal to the little q that experiences that force times an electric field. What does that mean for this problem? Well, we know that the electric field is created by a non-conducting sheet, and I know a non-conducting sheet has an electric field equal to sigma over 2 epsilon naught. So I can plug that in for the electric field, excuse me, and I have Q times sigma over 2 epsilon naught. And there we have a force on a particle Q due to a sheet with charge sigma. Sweet. You could switch this problem around. You could say that it's a vertical rod. We know the rod has lambda over 2 pi epsilon naught r. So as long as you knew r, you could say it's Q times lambda over 2 pi epsilon naught r. Great. So that is our electric force. Now let's go ahead and do the physics 1 just as a review. I'm going to have an x component for my tension, and then my other two forces are all either x for the electric force or all y for the weight. So we'll go ahead and sum our forces. First of all, in the x direction, in the positive x direction, I have my electric force. In the negative x direction, so to subtract, I have the tension. Be careful here with my angles. I want the x component of that tension, which means I need the angle off of the, well, the angle here is off the vertical. So the x component would be sine of that angle 40. I know that usually in physics 1, we stuck to and the x component being cosine, and that, again, that works, if you remember, 90% of the time. Here's a 10% of the time it doesn't work because the angle is given off the vertical. So just as a reminder, if I have an angle off a vertical, then I need to use sine for the x and cosine for the y. I just have to switch them. Okay, so this is going to be t sine of that angle. For me, it's 40. And they should tell me that it's hanging there and it's not moving. They don't actually tell me anywhere in the problem that it's not moving, but it shouldn't be moving. This should be just equal to 0. Cool. So this allows us to say that the electric force is equal to t sine of 40. And then we also need to sum the forces in the y direction. Again, we have a component of a tension. This time it's going to be up in the y direction, so it'll be positive. Since we had sine for the x, in the y we'll have t cosine of 40. And then in the negative y direction, we have the weight. So we'll subtract the weight, set it equal to 0, and then go ahead and solve. And we have t cosine 40 is equal to the weight. So here are our two equations. We are given the mass. We ultimately want to solve for the charge density, which the charge density is here, tucked into the electric force. So we're going to have to do a substitution there. And we can solve this any number of ways. The way that I like to solve a problem where I have a sine and a cosine and I want to get rid of the coefficient, in this case, the tension. I don't know anything about the tension. I don't want to know anything about the tension, so I'd like to get rid of it. You could solve one equation for tension and then plug it into the other. Or if you want to get a little crafty with it, you can do the first equation. We can rewrite just switching the two sides as T sine 40 is equal to the electric force. And we can write the second equation as T cosine 40 is equal to the weight. And then a very sort of nifty trick to solve this is to just divide the left sides by each other and divide the right sides by each other. So T sine 40 over T cosine 40, my T's cancel and I have tangent of 40. On the right-hand side, I have the electric force over the weight. All right. And then, yeah, and then I'm good to go. I can proceed from here. I'd plug in my electric force that I found on the last slide. That was Q sigma over 2 epsilon naught. And then I plug in for the weight, m times g. And they give me Q, they give me m. I know g is 9.8. I know epsilon naught is 8.85 times 10 to the negative 12. And I can plug those things in and solve for sigma. So, all right. So I'll go ahead and leave the rest of that up to you. But yeah, that's an application of sort of what we've been doing and a tie into physics 1. And that's about as much tie into physics 1 as we're going to do. I mean, the next problem, we have a little bit of a tie into physics 1 as well. But this is nothing that, nothing beyond just sort of the basics of physics 1. So in problem number 7, we have a large metal plate. So that is the first thing that I want to point out, is that it is a metal plate. So with a metal plate, that is a conducting plate, which means that the electric field in this problem is just going to be sigma over epsilon naught. Sigma over 2 epsilon naught is for a non-conducting plate. For a metal or conducting plate, it's sigma over epsilon naught. There's no 2 on the bottom. Okay, and in this problem, we have an electron that we are shooting directly at the plate. And they give us sigma and they ask us to find how far from the plate the electron must be shot. So here's a little diagram. We just have our vertical plate and we're going to have an electron. So it'll be a negatively charged particle that's shot at the plate. And on the diagram, they label it with V naught, but what they actually give us is the kinetic energy initial. So what we need to keep in mind with that is that we have to supply our own. This is the little bit of physics 1. Remember that kinetic energy is 1/2 mv squared, right? So our initial kinetic energy will be equal to 1/2 mv initial squared. So use that kinetic energy that's given. We use the mass of the electron. The mass of the electron is 9.11 times 10 to the negative 31st kilograms. So you go ahead and plug that in and isolate your initial speed. Okay, that's the thing that we actually want to find. And then what are we going to do with the speed? How do we tie this into an electric field? Well, I want to get from speed to field. How do I get from field to speed, speed to field? I would start thinking personally about motion. So I'm going to find a distance that this guy covers. And I want that ultimately to be, a delta x. And I'm also told that I want the electron to come to a stop right at the plate. So that would be a V final is equal to 0. All right, so I'm solving for a delta x. I know V final is 0. I know that I can find V initial right here. Hopefully that's enough there to sort of shake loose your physics 1 training to say, we want to do motion, right? So what else can we possibly find with the electric field? As far as motion goes, we have an electric field on the last problem. Remember, we related this field to a force, and just as it was in physics 1, force is equal to ma. So from F equals ma, and from our knowledge that the force is QE, we can rewrite this as QE equals ma. We had a homework problem in homework 1 like this, and here this is popping up again. Now, however, unlike in homework 1, now we actually want to supply our own definition for E. It's sigma on epsilon naught. So I have Q sigma over epsilon naught. is equal to m times a. And yeah, as I said, I want to solve for the acceleration. So solving this for the acceleration gives me q sigma over m epsilon naught. All right, so I have acceleration, I have v final, v initial, and a delta x. I need to do a kinematics equation then. Which one allows me to relate these four quantities? That will be v final squared is equal to v initial squared plus 2a delta x. That's your kinematics equation from physics 1. And you plug in your three knowns and solve for ultimately delta x in this case. So we'll be able to actually calculate this given our sigma in the problem and given the same mass for the electron. We can calculate that here, plug that in for A, plug in our V initial, and of course V final will just be 0 on the left-hand side, and then just solve for delta x. All right, so that's two problems where we integrate a little bit of physics 1. This is kind of our probably, well, I guess we did do one problem where we had a q equals ma last week, but this is, you know, another exposure to the way that physics 1 can sometimes kind of creep into physics 2 just a little bit. All right, so we've got one more problem here to go, one more application, and this problem is going to kind of have a lot of different stuff going on. And yeah, so we can sort of go ahead and tackle these different pieces. To start, we have two different materials. So we have a sphere that is solid, that is non-conducting, and it is inside of a spherical shell, which is conducting. Okay. So to start, here's our little non-conducting sphere on the inside. It's going to have a radius of a. And then outside, we have another sphere that is like a little shell. Maybe a, okay. And that shell is made out of metal. Again, it is conducting. That's pretty horrible, but there's some thickness to it. That's what those two different lines are. Try that again. Okay, that's not terrible. And this guy's going to have an inner and outer radius. So the inner radius is going to be B, and the outer radius is going to be C. In other words, it's metal with some thickness, but it is hollow on the inside, and inside of the hollow, there's that little yellow non-conducting sphere. Okay, so yeah, so they're going to ask us to find the electric field at all of these different distances. And the first one is starting off at the center. Now, what we need to consider as we sort of move through here is there's a few different phenomena going on. The first thing we actually need to do, I think, is parts G and H. I think that's where we have to start. So to start with, the sphere on the very inside has a charge Q. It's in femtocoulombs, which is femto, did I do that right? Femtocoulombs, which is 10 to the negative 12th. So great, so mine happens to be 7 femtocoulombs. Okay, so this is positive. I'm gonna use a different color on the inside here. So this is plus 7 femtocoulombs. And then the outer shell has a total charge, a net charge of negative 7 femtocoulombs. So I'll have negative 7 femtocoulombs on the whole thing. Now, something that I haven't covered yet, I very quickly alluded to it when we were talking about a conducting sheet. I said that the charge is going to distribute on the outside of the sheet. And this is going to hold for a shell as well. There's never any charge buildup inside of a conducting material. In order for the conducting material to reach an equilibrium state, the charge has to build up on the surfaces. So in the case of a spherical shell like this, you could have charge built up on the inside and you could have charge built up on the outside, but there should be no charge inside the actual sphere itself. Okay, what does that mean for this problem? Well, the other dynamic that's going on here is that the charge that is on the inside of that conducting shell, it has to be equal to the charge that is enclosed by the shell. So what I mean here is we have positive 7 femtocoulombs on that conducting sphere or non-conducting sphere in the center. That means that there has to be an equal and opposite charge built up on the inner piece of the shell. And here we have to have a negative 7 femtocoulombs. So that means that we have negative 7 femtocoulombs built up on the inside of the shell. And then that plus whatever is on the outer shell has to add up to this total. So for this problem, it happened to be negative 7. But let's say that they told us that the shell had a charge of negative 10 femtocoulombs built up on it. That would mean that that I still have negative 7 on the inside, but I would have an additional negative 3 on the outside. Now for this problem, because we have negative 7 already built up on the inside, and that is our total, that means that our net charge is 0 femtocoulombs. On the outside, I should say. It's not a net charge, that's just the charge that's built up on the outer shell. And that's, again, just because this number, which is induced by this value right here, because that number happens to be the same as this one, that's why we have 0 on the very outside. All right, next up, we want to calculate our electric field. For part A through F, we want to calculate the electric field at all these different locations. And as we do this, the important thing to remember, to go all the way back to the beginning of this chapter, is that we consider only the charge that is enclosed by a Gaussian sphere of the given radius. So for part A, where they give us a radius of 0 centimeters, a radius of 0 centimeters produces a sphere with no volume. It's not a sphere. There's no charge enclosed. So that's why that specific distance at r equals 0, right at the center of the whole arrangement, there is no electric field. In part B, we're asked to find the electric field at r equals a over 2. For this one, we are inside of our non-conducting sphere. So I'm going to blow up just the non-conducting sphere in the middle. It looks like this, right? Okay, and it's solid, so there's charge all throughout the whole thing. And they ask us to find the electric field at a location that is only halfway from the center. So right here, they're asking us to find the electric field there. And so what we do is we draw a Gaussian sphere that is defined by that radius. Okay, that's our Gaussian sphere. And the electric field will just be equal to kq over r, kq over r squared, where q is the charge enclosed within that sphere. So this is sort of putting together our two different pieces. Electric field is kq over r squared, and we know from Gauss's law that that's only the charge enclosed. So putting that together, we have k times the absolute value of q enclosed. Oops, that should have been an absolute value over epsilon naught. All right, so in part B, in order to actually calculate the electric field there, there shouldn't be epsilon naught in the bottom. Sorry, it's kq over r squared. That'll be an r squared on the bottom. Great. So all the work in doing this problem is just to find the charge that's enclosed by the sphere that I've drawn right here. And you'll notice that that sphere has a radius, well, it's defined to be half the total radius of the yellow non-conducting sphere. And so my charge enclosed, I can do sort of a ratio here because I'm going to have uniform distribution. So my charge enclosed over the total charge, which we'll use big Q, has to be equal to the volume enclosed over the total volume. And my volume enclosed is 4/3 pi r cubed, and my total volume is 4/3 pi r cubed. The only difference is what the r's are. So the volume enclosed is 4/3 pi times a on 2 cubed, and the total volume is 4/3 pi times a cubed. And so I can cancel a whole bunch of stuff out, and what I just end up with here is 1 over 8. So I have Q enclosed over Q is equal to 1/8. If I solve for Q enclosed, then I'll just have Q enclosed is equal to the total charge on the little yellow sphere, which is a Q1 in this problem. So it'll be Q1 over 8. So again, to write that down, my Q enclosed is equal to Q1 over 8. All right, and then what do we plug in for R? For just part B, we're investigating at a location of R equals A over 2. So we plug in A over 2 here, we plug in Q1 over 8 right there, and solve for your electric field. All right, then we continue outward. In part C, we go to where the radius is equal to A. When the radius is equal to A now, instead of being at a location that is sort of inside, now we are going to be at the edge of the sphere, of just the inner non-conducting sphere. And so the total charge enclosed out here is just equal to the total charge of the sphere. So we use the same equation for part C. We just have that Q enclosed is equal to Q1. In other words, all of the charges enclosed. We go out to, oh, and I should also mention that your R that you plug in on the bottom is just equal to A. In part D, we move out to R equals 1.5A. And since that will put us still inside, it'll be right here about, that's about 1.5A. Our Gaussian sphere out there still only encloses the little bitty yellow sphere. So our Q enclosed for part D is still just Q1, the charge in the yellow sphere. And our R in part D is 1.5 times A, but we're still using the same equation. In part E, we get out to a distance of 2.3A. The reason why that is an important distance is because that actually puts us inside of the conducting sphere. Now here's a rule that I've sort of alluded to, but just I'm going to say it explicitly now. Inside of a conducting material, the electric field is always 0. That's the fundamental rule. Inside of inside a conducting material, the electric field is 0. Okay, that is a reason why the buildup of the charge on the inner shell has to be equal to the charge enclosed. That's why you have equal and opposite. It also means that if you were to do a Gauss's law here inside the conducting shell, the enclosed charge now is the -7 femtocoulombs that's built up on the inner surface of the shell, plus the +7 femtocoulombs that is stored in the little yellow sphere in the middle. And of course, -7 plus 7 gives us 0. All right. Then the next location we do is all the way to the outside. When you go all the way to the outside, then now our Gaussian sphere encloses everything in here. So we just add up all the charge inside. But if you look at it again, you'll notice that I have, if I add up all of the charge, I have 0 femtocoulombs plus -7 femtocoulombs plus 7 femtocoulombs. Remember that these two together add to give us this. So somebody might be asking, wait, but why didn't I add this? Well, if you want to add this one, you can ignore these two. And then you just do this one plus this one, because this is just the sum of these two, right? So you don't want to add all three of them. This is just the total between those two. Anyway, point is, what is our total charge in region F all the way on the outside? On the outside, our total charge enclosed is also 0. So for both E and F, you'd have no electric field in those two regions. You could have a problem set up where you do have some electric field for part F when we are on the outside. All it would take is for there to be some buildup here. Instead of having 0 femtocoulombs, I would need something like even just 1 femtocoulomb on the outside would provide me some electric field outside of the whole arrangement. But inside the conducting material, the electric field is always 0. Okay, and that will do it for chapter 23. We've now done Gauss's law, and then we've done some applications. If you have any questions, as always, quickest way to get a response is to message me on Canvas. And if not, then have a good day, everybody, and we'll see you next week.